Welcome. Today I want to continue our discussion on aspects of energy and talk about energy changes or energy movement, or what we talked about as heat, right? The transfer of thermal energy in these different processes, these different physical and chemical changes. So the first thing that we want to remind ourselves of is that these physical and chemical changes involve energy changes. And the way that we conceptualize the movement of energy, right, between different objects or from one place to another, is to divide the universe, right, to divide things into what we call the system and the surroundings, right, where the system is the area of interest or materials reacting, and the surroundings is everything else. And so by looking at it this way, we can think about energy transfer or energy moving from the system to the surrounding or from the surrounding into the system when we think about that transfer of thermal energy. Now, one thing that we should sort of generally understand that will help us maybe picture this a little bit is that when systems have high potential energy, meaning they have a lot of chemical potential energy in most of our cases, right, they will tend to change in order to lower that potential energy. So in other words, they're going to transfer thermal energy to the surroundings. Now, we will see, both ways happen, right? But it's sort of a overriding theme that systems that have too high a potential energy will tend to try to minimize that potential energy. So with that being said, we have two types of processes that we can define. We have what we call an exothermic process, which releases energy into the surroundings. So in an exothermic process, energy is transferred from the system into the surroundings. In an endothermic process, right, just the opposite is occurring, right? We absorb energy from the surroundings. So energy moves from the surroundings into the system. So if we look at these pictorially, if we have an exothermic process, we're going to start here at higher energy, and over the course of the change, right, energy will be released, and what we end up with at the end of the change will be lower in energy, right? So energy would have been released from this system into the surroundings so that the material left at the end has a lower potential energy. In an endothermic process, right, we're going to start out here at a lower energy. Over the course of the change, we're going to absorb energy into the system from the surroundings, and so what we end up with at the end will be of higher energy or have more chemical potential energy than what we started out with. So, exothermic process, endothermic process. Now, when we think about this idea of heat, this idea of thermal energy flow or thermal energy transfer, right? That's what we think about as heat. So we're looking at heat flow, right? Thermal energy moving from one place to another, right? Is it moving into the system in an endothermic process or out of the system? But in either way, it's flowing. And so if we want to measure the amount of heat that flows or that moves in a particular process, we want to be able to calculate that heat. Now, before we can jump right in to calculate that heat, we need to introduce another concept, and that is something called the specific heat capacity of a material. So this is a property of a material, sort of like density, right? Right? This is a physical property of a material, and it is the quantity of heat, typically expressed in joules, sometimes calories, needed to change the temperature of 1 gram by 1 degree Celsius. So this is how much heat has to flow in or out in order to raise or lower, if we're flowing out, the temperature of 1 gram of a substance by 1 degree. And the units of heat capacity are typically joules per 1 gram per 1 degree Celsius. So joules over grams times Celsius. Now, if we look at a table of these heat capacities, kind of like what we looked at with densities, right, they give us a basis of comparing it. So in this case, right, it tells us how much heat it takes to raise and or lower the temperature of these particular substances. So the lower the specific heat capacity, the easier it is to change the temperature of something. So the less energy it takes to do that. So to change the temperature of, say, copper only takes 0.385 joules to change 1 gram by 1 degree. Now, on the other hand, if for aluminum, right, it takes 0.9 joules to raise 1 gram by 1 degree Celsius. And if you look at the far end of the scale, something like water has a very high specific heat, right? It takes 4.184 joules to raise 1 gram by 1 degree Celsius. So it takes a lot more energy to change the temperature of water than it does to change the temperature of, say, copper. And so that's really what the specific heat capacity can help us sort of look at. So how hard is it to heat up or cool down particular substances? So again, if I have a high specific heat like water, changing the temperature requires a lot of heat. Or right, we have to lose a lot of heat in order to cool it down. So this is the reason why when you go to heat up water on the stove, right, it seems to take a long time, right? Because we have to put in a lot of heat. A lot of thermal energy has to move in. We have to transfer a lot of thermal energy in order to raise up the temperature. It also takes a long time for water to cool down because we have to lose a lot of thermal energy for that temperature to change. So let's think about calculating heat. So the formula that we're going to use is to figure out how much heat. Now remember, heat is represented by Q. Right, so this is heat is going to equal M is the mass or the grams of material times the C here, right? That's our specific heat of the material, whatever that happens to be. And a delta T is the change in temperature. Now, the way delta T is calculated, so this will be important, is the change is always the final temperature, so the one that we're ending at, minus the initial or the starting temperature. So we always calculated final minus initial. So sometimes it's going to be a negative number, right? If the temperature is dropping down, then the change is going to be negative. And that's important because that'll give us a Q value, a negative Q, right? So a negative Q indicates a cooling down, right? Or an endothermic process, right? So it's losing heat, whereas a positive Q, right, is temperatures going up. And so this is going to be exo, or we're gaining heat. So the signs of Q, delta T, will help us understand what kind of process we're dealing with. So let's do a sample calculation here. So in this problem, we find that a 1979 copper penny. Now, the year is important there because in 1979 pennies were solid copper. In the snow, we pick it up, and we want to know how much heat it absorbed as it warms from -5 degrees Celsius to 37 degrees Celsius. And we're told that the penny weighs 3.10 grams. So we're trying to find out heat, right? Remember, Q. Right, so if we think about our equation, right? Q equals the mass times the specific heat times the change in temperature. So if we think about what we know, right? M is the mass, right? We know that M equals 3.10 grams, right? Our specific heat, right? If we look in our table, we look up copper. We have 0.385, again, joules, gram, degrees Celsius. And our delta T, remember, is the final temperature minus the initial temperature, which in this case, my final temperature, right, is 37. My initial temperature was -5. So I have 37 minus a -5. So we get 42 degrees Celsius. Now, it's important to have the 0 here, right? We're doing addition and subtraction. So our answer is going to be given to a certain decimal place. So this value goes out to the tenths place. This value goes out to the tenths place. So our answer must go out to the tenths place. So delta T equals 42.0 degrees Celsius. So now we have our values. So we're going to go, our amount of heat is going to be 3.10 grams times 0.385 joules. Remember, the number always goes with the top unit, per gram degrees Celsius. Delta T, 42.0 degrees Celsius. So if we think about units here, so I have grams on top, I have grams on bottom, those cancel. I have degrees Celsius on bottom, degrees Celsius on top, those cancel. So all I'm left with is joules, which is the units of heat, right? Heat are going to be in units of energy, and one of the units of energy is the joule, so this makes sense. So if we do our math, we calculate Q, our calculator is going to give us something like 50.127 joules. Now, significant figures, we have to keep count. So we're multiplying, so we look at the numbers that we used. So our mass has 3 significant figures. Our specific heat, again, has 3 significant figures. And kind of like density, we probably should think about this one because it's probably not an exact value, kind of like density's word. So we got 3 here, we have 3 here. So we're going to express this as 3 digits. So 501, the 2 tells me to leave it alone. So 50.1 joules would be my heat here. So this is one example for calculating Q. Now, we're going to close out with one more example that might be a little bit more complicated. And sometimes we won't be asked to find Q. We'll be asked to find one of the other values in our equation, like the mass or the specific heat or the change in temperature. And so, let's look at another problem. So we have 328 grams sample of water, absorbs 5,780 joules of heat. We want to calculate the change in temperature for the water, or in other words, the delta T. So if we look at our equation, right, our equation, remember, is Q equals mass times specific heat times delta T. So we have delta T we want to solve for. We have Q, we have M in T. So if I want to solve for delta T, I need to have Q. You could divide both sides by M. Let's erase this. Let's show this. So if we divide both sides by M, divide both sides by M, the M's cancel out here. If we divide both sides by C, the C's cancel out here. And so what we end up with is Q divided by M times C equals delta T. So if we look at what we know here that Q equals 5,780 joules. We know that M equals 328 grams. We know that C, if we look at our table for water, 4.184 joules per gram degrees Celsius. And so we have our values. We can put them in here. And so we have 5,780 joules divided by 328 grams. Now, one way to think about this, right, is this is dividing by 4.184 joules. And it's just like a conversion factor where this goes with the number, and that means the grams times degrees Celsius would go on the top to give us our delta T. So if we look at units, our joules cancel out top and bottom, our grams cancel out top and bottom and top, and so we're only left with degrees Celsius as a unit, as it should be. And so if we calculate this, we get 4.21 degrees Celsius equals my delta T. Now let's think about significant figures. So our heat has 3 significant figures, right? So that 0 is not significant. Our mass has 3 significant figures. And our heat capacity here has 4 significant figures. So we have to limit it to 3. So 4.21 is 3 significant figures. So this would be the way we would want to express our answer. So our delta T equals 4.21 degrees Celsius. Now what about if the water was initially at 25, what is the final temperature? Well, remember, delta T equals temperature final minus temperature initial. So if 4.21 degrees Celsius is the change, and the final is what we don't know, and our initial is 25.0 degrees Celsius. So if I want to get temperature final by itself, I'm going to add 25 to both sides. So 4.21 plus 25 equals the final temperature, which equals 29.21 degrees Celsius, or if we think about significant figures again, so since we're adding, we look at decimal places. This one goes out 2 decimal places. This one only goes out 1 decimal place, so our answer can only go out 1 decimal place. So our temperature final is going to equal 29.2 degrees Celsius. So a little bit more complex problem, but understanding that, within this equation, we can solve for any of the 4 different values if we know the other 3. And for temperature change, once we know that temperature change, we could figure out either the final or the initial if we knew the other one. Okay, so this again concludes our discussions on Chapter 3. We'll be moving on to Chapter 4 to look at atomic structure and atomic theory in the next section.